Okay, welcome back to what will be the Wednesday lecture for Wednesday, April 8th. I'm trying something a little new with the lighting. Hopefully it's an improvement. I know I'm not going to win any Academy Awards here, but hopefully it makes things a little bit easier to read. Announcements. It's amazingly warm out here today. 80 degrees. It's a beautiful day. And I thought about having class outside, but then all the neighbors are out, and I don't know. I couldn't find an extension cord. So, unfortunately, we're back in the basement. An important announcement about exams. So we are going to have an exam which will be of the kind of, well, of course, take-home variety. So it will appear in Gradescope. That's the plan. And the way it's going to work is that the exam will be available. So I will put all this in an email. But the way it's going to work is that the exam will be available for you to begin at any point during a fixed 24-hour period. Once you start the exam, you will have 2 hours to complete it, plus, I think, 10 minutes worth of time just to upload things and deal with the practical aspects of getting your exam online. Okay, so you have a 24-hour window. This is to account for people in different time zones all over the place, and for different schedules and all that sort of thing. The 24-hour window is scheduled to begin at the same time that the exam was scheduled to begin. Again, I will put all that in an email. And then you can begin the exam in earnest at any point over the next 24 hours. Okay, so that's the guidance from the department and from the university's provost. So that's really not subject to alteration, for better or worse. Yeah, so that's where things stand for the exam. If you have specific questions, you can ask them by email or on Piazza. Okay. Right. So, Chapter 5, Continuity. Big topic in real analysis, okay? So, let's just go ahead and start with the definition, okay? So, f, as usual, is a function from some domain A to R. Okay? We say f is continuous. I will abbreviate continuous CTS. Always. Force of habit. There's no way I can change it. But it also has the advantage of taking up a lot less space on my tiny chalkboard. And we'll have to use the word over and over again. So we say f is continuous at a point C in the domain A if for all epsilon greater than 0, so it looks a little bit like the definition of the limit. If for all epsilon greater than 0, there exists a delta greater than 0 such that the distance from f of x, not to some random number L, but to the specific number f of C, is less than epsilon if x, first of all, belongs to A, right? That's important because we would like for f of x to be defined, and in order for it to be defined, x should belong to the domain of f, okay? So if x is in A and the distance from x to C is less than delta. Okay? So, similarities, differences with the definition of the limit. Okay, so similar to the limit in that you are given a tolerance epsilon greater than 0, and you would like for the distance between your function and some fixed number to be strictly less than epsilon. Difference is that rather than just be some random number L, now the number you want to be close to is exactly the value of the function at the point C, okay, and we're insisting, this is another difference, that C actually belongs to A, okay, C actually belongs to the domain of the function f, whereas in the definition of the limit, you'll recall C only had to be, and indeed did have to be, a cluster point of the set A. Okay, here C does not have to be a cluster point. C can be any point in the domain. However, it's also true that A might have cluster points that are not in A. You cannot discuss the continuity of this function f at those cluster points because the function f is not defined at those points. Okay? Right, so we want the distance from f of x to f of c to be less than epsilon if, again, similar to the definition of the limit, if the distance between x and a certain value c is less than delta. But a difference here is that we no longer insist that x be different from c. Okay? Could be equal to c, that's fine. And another small difference is that we insist, of course, that x be in A. Actually, that's not really a difference because x would have to be in A in the definition of the limit too. So that's not a difference. Pardon me. But this is, okay? So we no longer have this greater than 0 inequality. So that's the definition of f being continuous at a point C in A. All right? We'll drink that in. All right. Now, as with virtually everything to do with limits of functions, we can always use the fact that a limit of a function can be characterized sequentially to give, so, I mean, as I said, this is strictly speaking not a definition that involves a limit, but it's very, very similar to the definition of a limit, okay? And because of that, there is a sequential characterization of when a function f is continuous at a point C in its domain, and we will give that now. Okay, so alternatively, f is continuous at C in A if for every sequence xn in A, so every element of the sequence should come from A, such that xn converges to C, we have that f of xn converges to f of C. Okay. Oops. So for every sequence in the domain A with the property that the sequence converges to C, we have that f of that sequence then converges to, whoops, I should say f of C. This is actually kind of handy. Okay. Again, this looks awfully similar to the sequential characterization of what it would mean for the limit of the function f as x approaches C to be equal to f of C. But again, there are some differences. Right? So once again, we are insisting here that the point C be in the domain of f, right? Rather than just be a cluster point of A. And the other thing that's different here, this is an important point, is that we're not insisting anymore that xn is not equal to C. Right? So you can have this sequence, and it's okay for the xn's to be equal to C. And this is the analog of, in the other definition, where we had x minus C is less than delta, but it no longer has to be greater than 0. X no longer has to be different from C. So what I would like to point out here is that in your first year calculus textbook, you know, in the great ponderous tome, Early Transcendentals, the definition of continuity that you get is this one. The f continuous at C in A, where here, once again, A is just the domain of f if the limit as x approaches C of f of x is equal to f of C. I mean, they typically break it up for whatever reason into like 3 steps, like f of C has to exist and the limit has to exist and f of C and the limit have to be equal. I mean, all of which are summarized in this single statement. So I have no idea why they break it up into 3 separate statements. However, right, this definition here involves a limit. Involves this limit over here. You have to be able to compute the limit as x approaches C of f of x. And now, of course, C is in A, but you can only compute the limit as x approaches C if C is also a cluster point of A. Okay? So this definition for continuity only works if C is a cluster point. Okay? And of course they don't tell you that. It's not clear whether they just glossed over it or what. But the idea is that in first year calculus, it doesn't really matter, because what are the domains of your functions? Inevitably, I mean, I'm struggling to think of an example otherwise. Inevitably, the domains of the functions you're talking about are, at their most complicated, a union of a few different intervals. Okay? And intervals have the property that every element of the interval is a cluster point of the interval. Okay? So as long as you're restricting your attention to functions f whose domains A are intervals, this definition is okay. Where you would get into trouble is when the domain of your function f has an isolated point. So let's say this definition breaks down if, say, for example, A is equal to the union, say, of just the singleton, the single point set 0, together with the open interval from 1 to 2. Okay? And why is that? Well, now your domain has an isolated point. That is, it has a point in it which is not a cluster point. Okay? Which means that in this definition here, this thing doesn't make any sense. You can't take the limit of your function f as x approaches 0. However, the two equivalent definitions I gave you at the beginning of the class for continuity, they both work, hold up, and will tell you that your function, in fact, no matter which function you define on this set here, it might be poorly behaved over here on this interval. But if it's defined at 0, it's automatically continuous at 0. So one consequence, and this is maybe one of those great exercise for the student things, so yeah, let's write exercise for the student. If A is finite, and C belongs to A, whoops, if A is finite and F is a function from A to R, then F is continuous at every C belonging to A. Okay? So functions on finite sets are automatically continuous everywhere. And this brings up a point that I really, really want to stress. Okay? Which is the following. There's writing down in capital letters. It is that continuity, by definition, is a point-wise concept. Okay? Continuity for a function is a question you ask about one point at a time in its domain. Okay? So the glib statement that such and such a function is continuous is just a shorthand for saying the function is continuous everywhere that it is defined. Because our definition of continuity only applies to a single point in the domain, okay? If you want to say the function's continuous, that's really just a shorthand way of saying the function is continuous at every point in its domain. Right, so continuity is a pointwise concept. It happens one point at a time. Alright, so, well, having made a big deal out of that, I will then nevertheless quickly write down the definition of what it means to say that a function is continuous on a set rather than simply at a point, because we do, practically speaking, wind up saying that a lot. So definition, once again, f is a function from a to r, and b is going to be a subset of a. Okay, so a set which is contained in the domain of a. Then f is said to be continuous at, continuous on B if f is continuous at every C belonging to B. Okay? So saying that a function is continuous on a given set is just a shorthand, a verbal shorthand for saying that that function is continuous at every point in that given set. All right? So, I went out today for a jog, and I didn't bump into anyone anymore, but I saw my neighbor on her front step, and she has, what would seem at first blush to be a very, very nice and very important, well, it is a very important administrative job, but at this very moment in time has got to be one of the most demanding jobs at the university. So she is, I believe, the vice provost of student affairs, which means somehow that when it comes to any serious problem that any undergraduate might have, the buck kind of stops with her. Needless to say, lots of students around the world have had their share of issues. So she's been putting in, she looked a little tired. She's been putting in some long days, and she was describing to me the fact that she had just heard about a student who was trying to get a hold of their academic advisor, and they were calling them from a quarantine camp in Vietnam, and the connection was terrible and so on. So these are the sorts of problems that some of your fellow students are dealing with. I have so far not heard about any critical access issues from any of you. Please, if there is a problem, if you are having some kind of access issue, then by all means, email me, get in touch with me, okay? And let me know before it's too late. And since we're on a little break here, this would be a good time to mention that I looked at the calendar, and so after today's class, then we'll have Friday's class, and then there are 2 more weeks of actual instruction, and then there's 1 week which is dead week. Now, normally, since of course you're not supposed to really assign new material or even really cover new material, during Dead Week, I would dedicate those 3 classes in Dead Week to a review. But that review tends to be kind of interactive. I think I will instead. Okay, so here's my suggestion, and I would like to hear feedback if you have it. But what I propose instead is that in lieu of notes for that week, I will write up a non-exhaustive. It will come with a disclaimer that this is not necessarily everything you need to know, but it will certainly be a list of the things you absolutely should know. A sort of review kind of set of notes, that will hit the high points for the course so far, and then normally what I would do during that review week is give you a kind of outline of the stuff that, of course, you need to know. But I would also entertain a lot of questions. If you have a question about a particular topic, feel free to ask, and things would be very interactive, I would hope, if we were in session. We're not. So what I'm thinking is that instead of just recording 3 lectures where I drone on about going over a set of notes that I'm going to post anyway, maybe I would instead try to set up, I have to make sure that this is possible. I think it is, though. So the university uses WebEx. And what I would try to do is set up a few WebEx meetings where you could participate and you could ask questions that you might have, kind of like a remote office hour. And I would endeavor to set up some, 3 of these, say, during Dead Week for a couple of hours each, and have them at significantly different times of day, sort of morning, noon, and later in the evening, so that hopefully, no matter which time zone you're in, at least one of those WebEx question and answer sessions will fit your schedule and your needs. So, that's the plan. Again, I will write to you in an email about the plans for the final exam and about the review week plans, but if you have an opinion on that, or you have some strong feelings, or you're worried that you're not going to be able to ask the questions you want to ask, then let me know, and let me know what the obstructions are and how we could maybe get around those obstructions. Okay? All right, back to work. So, that's 2 different definitions of continuity, and stressing the idea that continuity is a point-wise concept. Okay? Now, having defined continuity, we should also write down explicitly what it means to fail to be continuous, for a function f to fail to be continuous at a point in its domain. And, strictly speaking, this is just a matter of logically negating the 2 statements that I've already put up, the 2 alternative definitions of continuity, but let's make them explicit. So, f, of course, is a map, a function from A to R, and C belongs to A. F is not continuous at C if. So there will be 2 alternatives. The first one is going to be the logical negation of the first definition of continuity I gave you. The second one will be the logical negation of the second definition of continuity I gave you. Okay, so if there exists an epsilon naught greater than 0 such that for every delta greater than 0, there is some element x delta belonging to A such that on the one hand, the distance from x delta to C is small. It's less than delta. Yet, the distance from f of x delta to f of C remains bounded away from 0 by this number epsilon naught. Okay. So again, this is similar to, but not identical to, the statement we have for the limit of a given function being not equal to a fixed number L. Okay? So this says that f is, not continuous at f of C. Right? That's the negation of the first definition. Now, you can go ahead and negate the second definition. So it's the same preamble. But it has the following formulation. If there exists a sequence xn in A such that xn converges to C, yet f of xn does not converge to f of C. That's a little more succinct in this case. So there's a sequence converging to C. And I would point out in particular that that means that, you know, a failure of continuity. So one way to see, I was saying earlier, right, if you have an isolated point in the domain, then the function's always going to be continuous at that isolated point in the domain. So how can you see that? Well, let's suppose that C here were an isolated point in the domain. The only way that our function f could fail to be continuous is if we were able to find a sequence in the domain, if we were able to find a sequence in the domain converging to C such that f of that sequence does not converge to f of C. But C is an isolated point, meaning that any sequence xn from A that converges to C, in fact, eventually has to be equal to C for every n beyond a certain point. Okay, you can't get as close as you want to C without actually being equal to C. Right? There's no approach to C. That's what it means to be an isolated point. Which means, so if every element of this sequence from a certain point onward is actually equal to C, then it means that every one of these f of xn's from a certain point onward is actually equal to f of C. In particular, you will definitely have convergence. There's no way this can fail. Okay, so that's one way to see, for instance, that if C is an isolated point of the domain of your function f, then f has to be continuous at that isolated point, by definition. Okay, so those are two different characterizations of discontinuity. Let me see. All right, now for a few examples. So these first examples are just going to be, a list of things we already know, more or less, but let's write a few of them down. So, some examples. A constant function is continuous everywhere, okay? The identity function, that's continuous everywhere. The function f of x equals x squared, that's continuous everywhere. And how do I know these things? Well, I told you that this definition of continuity that you get in first year calculus isn't, strictly speaking, the proper definition. And I explained how having, oh, curses. I left my phone upstairs because I knew there was an alarm on it, but I left it right on the granite countertop, which is drilled directly into the roof beam over my head. So I'll be right back after I turn this off. All right, I'm back. And it got me thinking, if you're ever at a point in your life where you have to decide, should I get granted or not? The answer is always yes. Yes, you should. Doesn't matter. Sell a kid, remortgage the house, get the granite. It's awesome. There is nothing you can do to it to destroy it. But if you get it, you can never cook in anybody else's kitchen ever again because you will ruin their countertops. You'll get so used to putting hot things everywhere that, yeah, I speak from experience. Anyway, so, as I was saying, the definition of continuity that you get in first year calculus, right? It's this limit as x approaches c has to be equal to f of c thing. And I explained that only works if C is a cluster point of the domain. But in each of these three examples, the domain is all of the real numbers, and therefore every point in the domain is a cluster point of the domain. Therefore, the sort of basic, training wheels version of continuity that you get in first year calculus actually does work, and therefore, based on limits that we have already found already in this class, these statements then hold. These three functions, these are all continuous. And of course, there are lots more examples, but we will get to that when we start discussing combinations of continuous functions, which we have not gotten to yet. What I wanted to discuss before the end of this class is a particular example, a sort of interesting example. Oh, are you serious? I'll be right back. Alright, I live my life by alarms, you know. I realize that at some point in the not too distant future, I'll probably have a daily alarm to remind me to take my memory pills. Won't that be nice? Alright. So, I wanted to give you this example, because it's kind of a fun example for all kinds of things, actually. So let's consider the following function. Let's say that f of x is equal to 1 if x is a rational number, and 0 if x does not belong to the rational numbers. Okay, so if I were to draw this thing, I mean, it's kind of impossible to actually draw it, but basically it kind of a whole bunch of dots here. So over every rational number, there's height 1. Over every rational number, you get a value of 1, and everywhere else the function is equal to 0. What can we say about this function? Well, so it turns out that this is an interesting example for all sorts of questions in calculus. I mean, for one thing, you could ask, does this thing have an integral, right? So typically we think of the integral of some function as being the area underneath the curve. Well, there's not much of a curve here, right? More just a collection of dots. So it doesn't make any sense to even ask, what the integral might be. And in fact, it turns out that not only does it make sense, but this example here actually informs the definition of the integral to a degree, the integral for grown-ups. So just like everything else in mathematics, that definition of the integral we gave you with the Riemann sums and all that stuff, it's all nonsense. Right? Or at least it's kind of the training wheels version of integration. I mean, it is not a version of integration that leads to some of the most important and powerful and useful theorems in mathematics, especially applied mathematics, things like Fourier analysis and stuff of that nature. Yeah, so sorry about that. But this function is also curious because you can ask, well, I mean, what about continuity? So continuity is a pointwise concept, so we could ask at any given point here along the x-axis, is this function f of x a continuous function? And the answer is no. So f is not continuous at any real number. Okay? So, how do we see that? Let's see if we can squeeze part of the explanation in here, keep it all on one board. Well, here's the idea. So we'll use this second sequential criterion for the failure of continuity, right? And that criterion said f will fail to be continuous at a point if you can find a sequence in the domain converging to your given point such that f of that sequence does not converge to f of the given point. So let's say let C belong to the rationals so that f of C is equal to 1. Okay? And then the point is that we can use the density theorem here. So by density, there exists say an xn converging to C such that each xn fails to belong to the rational numbers. Okay? All right, so this is a consequence of the density theorem. If you take your rational number C, and you take any little neighborhood around C, you can always squeeze an irrational number in there somewhere. And so you just take a whole sequence of those irrational numbers, getting closer and closer to C, and there you go. A sequence xn converging to C such that all of the xn's do not belong to the rationals. And what that means is that so f of xn, right? So those are all irrationals, which means that f of those xn's has to be equal to 0. And that, of course, does not converge to 1, which is f of C. Okay? And that's exactly what it means for continuity to fail at the point C. We found a sequence xn converging to C such that f of xn does not converge to f of C. Now, if the roles are reversed, right, so if C does not belong to the rational numbers, then density again will tell you that instead you can find a sequence of rational numbers xn converging to C such that each of the xn's, well, okay, is rational. And then instead you'll have that that f of xn is equal to 1, and 1 does not converge to 0, which is equal to f of C. Okay, so you can turn that around if C does not belong to the rational numbers. But the upshot of this is that using the sequential criterion for the failure of continuity, you can show that this function f is not continuous at any C in R. So continuity can fail really badly, and the function itself is actually really straightforward to define. Okay? All right. So I guess in the couple of minutes I have left, I'll just preview what's going on. So with that example, that concludes section 5.1, which is just on the basic introduction to the definition of continuity. So next time, we'll look at section 5.2, and this is combinations of continuous functions. Okay. And in keeping with the theme of the limit laws, say, for limits of functions, right? These combinations of continuous functions, things like what happens when you add two continuous functions, when you multiply two continuous functions, divide two continuous functions, all of those statements essentially amount to the corresponding statement about limits of functions, which in turn correspond to the corresponding statements about limits of sequences. So there's nothing of substance to prove here, okay? And everything you expect to be true will be true. You know, if you have two continuous functions on a given domain, their sum is continuous, their product's continuous, and their quotient is continuous, provided that the denominator is not 0. The thing that we will spend a little bit more time on, which is important as well, is composition of functions. Okay, so what does it mean, once again, to compose two functions, and then how does one characterize exactly when, so if you have two functions, you're going to compose them under what conditions is the composition continuous at a given point in the domain of the original function. Alright, so that's what we will be covering next time. Again, if you have any questions, concerns, access issues, anything at all, just email me and wash your hands. Alright, I will see you next time.